Okay, let's look at this problem. Io, one of the moons of Jupiter, orbits Jupiter with an average radius of 421,700 kilometers and a period of 1.769 days. It's quite fast. So, so in comparisons, the Earth's moon goes around it in 29 and a half days, something like that. And the orbital radius are roughly the same. Based upon this data, what is the mass of Jupiter? So the faster the moon goes around, we saw that the more massive Jupiter must be. So Jupiter is much more massive than Earth, and we know that. Okay, so what is the mass of Jupiter? Okay, so let's do this. So here's Jupiter, here's Io, and here's the orbital radius. Okay, so we should have the centripetal force is being provided by the gravitational force. The gravitational force provides the centripetal force, so mv square by r should equal gm mass of Jupiter divided by r square. One of the r's cancels and the m's cancel. So mass of Jupiter, what are we trying to find? We are trying to find the mass of Jupiter. Okay, so mass of Jupiter is equal to v square r divided by g. Okay, so we can find v from this data, the period and that, and the radius is given and g is known, so we should be able to calculate the mass of Jupiter. Okay, v is 2 pi r, the distance covered, which is one orbit, divided by the period. Okay, so we are going to substitute this in there. And since we need v square, let's just do that. 4 pi square r squared over t squared. So mass of Jupiter is 4 pi square r cubed g t squared. All right. So essentially, we've derived Kepler's third law. Kepler's third law has something to say about t squared by r cubed for satellites. Okay, and that ratio is constant for planets and satellites. It's related to the central mass. Anyway, all right. So let's put in the numbers now. But before we do that, let's add a page. Okay, so here we go. And okay, let me copy this formula and put it in the new page. All right, now we're ready to put in numbers. So this is 4 pi square r cubed. R is 4.21, that's in kilometers, 21 times 10 to the 5 kilometers, so we'll make it 10 to the 8 meters. Okay, cubed, g is 6.67 into 10 to the minus 11 Newton meter square kg square, and period is 1.769 days. 1.769 days. Each day has 24 hours. Each hour has 30,600 seconds squared. Okay, so there is the mass of Jupiter. And the combination of all these units should work out to kilograms, of course. So, and I'm not going to. So if you put newtons as kilograms, meters per second square, one of the kilograms cancels, the other kilogram will be left there. You'll get meter square, and the second square will cancel. Okay, so you can do all of that. But let me take care of powers of 10. So here is 8. 8 times 3 is 24. And then with 11 coming up, 24, that's 35. Okay. And okay, so here's 3.6 times 10 to the 3. So I'm going to borrow that. 3, 4. 4 squares at 4 times 2 is 8. 35 minus 8 is 27. Okay, so 10 to the power 27 kg. 4 pi square 4.21 cubed divided by 6.67 times 1.769 times 2.4 times 3.6 squared. So that's the numerical factor. Okay, so let's evaluate this. All right. .769. Okay, so the numerical factor works out to 1.89 into 10 to the power 27 kgs. Okay, that's mass of Jupiter. Now we'll just compare it to the mass of Earth just to get a sense for it. Mass of Jupiter over mass of Earth is 1.89 into 10 to the 27 kg divided by 6 times 10 to the 24 kg. That's the mass of Earth. Okay, so essentially we'll borrow 3 zeros here, so 1890 times 10 to the 24 kg. That'll cancel that. All right, so 1890 divided by 6. Okay, so Jupiter is 315 times as massive as Earth. Okay, so that's what we found. Okay, that ends this problem.